All right, so we're going to look at Giancoli 6-7 and its conservation of mechanical energy. So here we got a rock at a certain height. As it drops, it loses its potential energy because it loses height, but it also gains speed, which means it gains potential energy until it gets to the floor. And when it hits the floor, it has no potential energy because it has no height, but it has its max speed, which means it has the most kinetic energy. But since mechanical energy is always conserved, potential energy we start with equals kinetic energy we end with. And anywhere in the middle, the two added together will equal that number also. And that's what we have to assume happens. So if we have a roller coaster, if there is no friction, again, no non-conservative forces, the speed of a roller coaster will depend only on its height compared to its starting height. So here, no speed. Here, a portion of the speed. Here, full speed, right? Or max speed, if you will. And again, potential, kinetic, combination of potential and kinetic. For an elastic force, conservation of energy also applies. So here we got a pole vaulter, and here you got ground zero, so no potential energy, but you have max speed, so you have kinetic energy, and then you have this kinetic energy being converted into elastic energy, into potential energy. So these two together, the bend of the pole, the elastic potential energy, and the kinetic energy work together to convert to total potential energy at the end. So here's some examples. A falling rock. If the initial height of the rock is 3 meters, so up here is 3 meters, what is the rock's velocity when it is 1 meter above the ground? So somewhere in here, okay? And we just use energy to solve that. Do it now.
All right, so we have the height of a rock is 3 meters, and we want to find the velocity for when it has fallen to a point where it's 1 meter above the ground. Okay, so as it falls these 2 meters, we want to find the velocity. So first off, my velocity here is 0, and I want to find final velocity. So you can use kinematics if you want to. I'm going to use energy. You can test me by using kinematics if you don't believe energy. But at the top, we just think about the energies that we have. Due to height, we have potential energy due to gravity, and we have kinetic energy, but since velocity is 0, there really isn't kinetic energy. So at the top, I have potential energy due to gravity. As it gets to 1 meter above, there's still potential energy due to gravity, but since it has a velocity, there's also kinetic energy. So my equation is going to be potential energy due to gravity initial equals potential energy due to gravity final plus kinetic energy final. Once I have that, then I substitute. So I got mgh, and this is going to be initial height, mgh final height, plus 1/2 mv squared final. Sorry, mv final squared. All right, so let's start substituting in. 1, since I have mass in each of these, I can substitute as 1 or just eliminate mass, which I'll do. G is 9.8, and my height is 3 meters initial. Gravity is still 9.8. My height is now at 1 meter. And my velocity at the bottom is what I'm solving for. So now I just algebra from here. I'm going to assume that you can do this algebra. So I get 29.4 joules. I get 9.8 joules plus 1/2 Vf squared. I subtract this over. Divide by 1/2, and then take the square root, and I get the final velocity to be 6.3 meters per second. So it has a final velocity of 6.3 meters per second after it has dropped that far.
Roller coaster car speed using energy conservation. So we have a height of a hill being 40 meters, and the car starts from rest. We want to find the speed at the bottom, and at what height will this car have half the speed that it does at the bottom. And we want y equal to 0 at the bottom of the hill. So all potential all kinetic, and then somewhere in between, right? Do it now.
All right, so we have the roller coaster car up here, 40 meters height, and it's starting from rest. It goes down to here, to 0 height. How fast is it going? And then when we get up to here, we want to see what height the roller coaster will be if its velocity is half of what it is down here. So we choose a 0 point to be the bottom of the hill, as it tells us in the problem. We would do that anyway. And then we just figure everything else out. So this car at the top, since it has no potential energy, or has no kinetic energy because it starts from rest, is going to have only potential energy. Here at the bottom, since it has no potential energy, this will only have kinetic energy. And then this one is going to have a combination of gravitational potential energy and kinetic energy. But since there's no friction, the energy I start with here will be the energy I finish with here. Okay, so let's go through the steps. So I'm going to compare these two, right? And I know the potential energy due to gravity that I start with will equal my final kinetic energy. So this is going to be mg h initial, and this would be 1/2 m v squared final. Again, masses are irrelevant, so I go 9.8 times my height of 40 equals 1/2 vf squared. So I can solve my final velocity. 9.8 times 40 divided by 1/2 square root, and it's going to be 28 meters per second. So my final velocity is 28 meters per second. So now, at the bottom I have kinetic, at the top final I have both. So kinetic energy initial, right, is equal to mass g height final plus 1/2 mass vf squared. So my kinetic energy initial is going to be 1/2 m 28 squared. This is going to be m times 9.8 times whatever that height is, plus 1/2 m times half of 28, so 14 squared. My m's cancel again. So I want to solve for HF, so I solve this. I go 0.5 times 28 squared. Then I subtract this, which is 0.5 times 14 squared. And I get 294. I divide it by 9.8. And the height where that's going to happen is 30 meters. Pretty quick to get that information. If we were doing kinetics or kinematics, it would take a heck of a lot longer.
Okay, we got 2 water slides. 2 water slides in a pool are shaped differently, but at the start, let's start at the same height. So 2 riders start from rest at the same height on different slides. Which rider, Paul Corian, is traveling faster at the bottom, and which rider makes it to the bottom first? Ignore friction and assume both slides have the same path length. So if potential energy is the same when they start, then they're going to have the same kinetic energy at the bottom. Okay, so their speeds are going to be the same. But now which one makes it to the bottom first? Well, if we look at the paths taken, this path is a lot shorter than this path when we talk about as we talk about switching velocities. Like we start here, go really fast, then we slow down, then we go really fast again. Here it's slow, 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 and fast. Corian should reach the bottom first, but again, they both will have the same speed at the bottom, even though Corian will get there faster. Okay, so toy dart gun. A dart of mass 0.1 kilograms is pressed against the spring of a toy dart gun. The spring with spring stiffness constant of 250 newtons per meter, and mass that we are going to ignore is compressed 6 centimeters and released. If the dart detaches from the spring when the spring reaches its natural length, what speed does the dart acquire? Do it now.
So dart gun, mass of dart of mass of 0.1 kilograms is pressed against a spring of a toy dart gun, as shown in the diagram. The spring with a stiffness constant of 250 newtons per meter with ignorable mass, so the mass of the spring not important, is compressed 6 centimeters and released. If the dart detaches from the spring when the spring reaches its natural length, then what speed does the dart acquire? So here's before, here's after. So before, when the spring's compressed, right, all we got is potential energy due to the spring. At the end, the spring has no more potential energy because it's been all turned into kinetic energy. So potential energy spring is what we start with. I'm going to say spring initial equals kinetic energy at the final. Potential energy of a spring, 1/2 k x squared. Kinetic energy, 1/2 mv squared. And we're trying to find this final velocity, right? So as I substitute in, my k is 250. And then my x is 6 centimeters, so I want to move the decimal 2 to the left. 0.06 meters is equal to 1/2. Now the mass is given to me, which I needed to have. Since I didn't have it on both sides, I couldn't eliminate it. V final squared. So there's my equation. And now it's just solve. 0.5 times 250 times 0.06 divided by 0.5 divided by 0.1, and then take the square root of that, and I get a final velocity of 12.2 meters per second. So that dart is leaving the gun at that velocity.
Two kinds of potential energy. A ball of mass 2.60 kilograms starts from rest, falls a vertical distance of 55 centimeters, strikes a coiled spring which compresses 15 centimeters. We want to find the spring stiffness constant of the spring. Assume the spring has negligible mass and ignore air resistance. So we're going to measure all distances from the point of where the ball first touches the compressed spring. So this will be 0.0. So we have a height that it drops, and then we have a compression point, okay? We'll do it for you. Do it now.
All right, so we have a ball with a mass of 2.6 kilograms dropping 0.55 meters to a spring below that gets compressed into 0.15 meters. And we want to know the spring constant of the spring based on that information. To do this, we will have to do a couple things. First, we want to go from here to here, okay, and find our velocity of our ball right before it hits the spring. And then we want to go from here to here to see how far the ball gets and find the spring constant. Now, to do this correctly, we do 2 steps. You can do it all in 1 step. I'll leave that up to you to figure out. I'm going to do it 2 steps so you can see more work being done. But we're going to start off with potential energy due to gravity, and we're going to finish with kinetic energy. So we want to find the ball right at the 0 point of our drop, which is right before it hits the spring, as it says in the problem. So we got potential energy due to gravity, initial, and kinetic energy, final. So mg, right, h initial, 1/2 m vf squared. Okay. So let's see what we know. Since our masses are the same, I don't need to put those into this equation to find out velocity. But our g is 9.8. Our h is 55 centimeters, or 0.55 meters, so 1/2 vf squared. Do the math on your calculator, and you get 3.3 meters per second to be your vf. Okay. So we know our final velocity. So we know here right before it hits the spring, it has a final velocity of 3.3, okay? It's at the 0 point, so all it has is kinetic energy. Now, as the spring gets compressed, 2 things happen. We get potential energy from the spring, and we get potential energy due to gravity because we're going below our 0 point. And so we have to account for both of them, which is okay. We just make our equation, kinetic energy initial equals potential energy spring final plus potential energy of gravity final. So kinetic energy, 1/2 m v squared, our initial velocity squared, our spring, 1/2 k x squared, and then plus mgh. So let's substitute in what we know. We got 1/2, our mass is 2.6, our initial velocity is 3.3, our spring k is what we're solving for, our compression is 0.15 squared, plus 2.6 times 9.8 times, now our 0 points here, so as we go down 0.15, it becomes negative 0.15. So I'm going to do an extra step here with the math so you can see it. 0.5 times 2.6 times 3.3 squared, okay, 14.2, all right, is equal to, and I'm going to keep this as is, plus 2.6 times 9.8 times 0.15, but that's going to be negative 0.15, so it's minus 3.82. All right, so that's what we're going to have. So now I'm going to add 3.82 to each side, then solve for k. So I won't do it all on the board, but I add 3.82 to my 14.2, divide by 0.5, divide by 0.15 squared, and then take the square root. I'm sorry, no, just keep my answer as is, right? And I'm going to get 1600. So my answer is going to be 1600 is going to be my spring constant. Now, why this is different, okay? And is that we break it into two parts, right? You could try to do it all in one part, and essentially what you would do is you would find your potential energy up here, and then that would equal this. So it'd be this would equal this, and you would still get the same answer, okay? It would still work out. So you could do it all in one step. I did it in 2 steps just to show you how to do some different figuring out. But the important thing is to understand is that if we make this our 0 point, then if we go below it, we have to account for that potential energy difference. And since it's going below 0, it's going to be negative. And that's how we can get our spring constant. So a little different, but something to look for if you see a problem similar to this.